In this video, I'm going to be assembling and testing this ZIF IDE SSD that I've designed for use in machines that use ZIF IDE hard disks, such as the 2008 MacBook Air, Sony Vaio UX UMPCs, or what have you. So like I said, this is a custom design that I designed myself, and the reason I've designed this myself is because the only alternative to something like this is a compact flash card, which are ridiculously expensive for some reason, or one of those really sketchy Chinese ZIF IDE hard drives. They also make ones for like 2.5-inch laptop IDE and what have you, but those are also overpriced, and the quality on those is not all that great. So with that said, I've decided to design my own using the best parts I could possibly source to make it as reliable as possible, as well as be able to make it relatively cheaply. Now, of course, I won't be able to make it as cheaply as, like a regular SATA SSD, at least for the capacity that this will support, but it is still better than the options that are already available. So with that said, like I said, I'm going to have to fully assemble this drive myself. So I'm going to do this in basically 3 parts. The first part is I'm going to install all the passive components, such as all the capacitors, resistors, this voltage regulator IC up there, and LEDs and what have you that I have on this board design. After that, I'm going to solder the connector up there, and then lastly, I'm going to solder the controller, which is based on the Silicon Motion SM2236 controller. That is what I designed this board to use, and as well as the 4 NAND chips here. So with that said, I'm going to go ahead and get the camera mounted in the tripod. I'll show you all the components that I have for this PCB, and then we'll just go through the process of assembling it. Alright, so as you can see here, I've gotten all the parts together that I'm going to be using to assemble this board. As you can see, it is quite a lot of parts. There are quite a few different value components that I need, such as resistors, capacitors, and whatnot. And then, of course, over here, I've got the chips, the NAND chips, as well as the SM2236 controller. You can see that right here. Flip it over. You can see that that is the SM2236 right there. And then these NAND chips I had to ensure were compatible with the SM2236, so any NANDs you put on this board have to be compatible with the controller, so that way they can be properly programmed and utilized as intended. So with that, we can just go ahead and begin assembling. Oh, one other thing I wanted to show is the program I used to design the board actually has a functionality to export a BOM in the format of an HTML document. So I have a list of all the components that are on the board and what values I need to put on them. So I'm just going to go through this list, find each component, and install it to the board. So with that, I'm going to go ahead and get the camera mounted up here, and then we'll begin the process of installing the passive components onto the board. Alright, so as you can see here, I'm now ready to begin soldering components onto the board. So before we solder anything, the first thing I need to do is apply some flux to the board and then tin all the pads that we're going to be soldering to. So in order to do that, I'm just going to use my soldering iron and just some solder and apply it to all the necessary pads. So like I said, we'll just start with flux. Alright, so as you can see there, I've gotten all the flux applied to pretty much every pad on the board. So now we'll just go over it, like I said, with some solder with the soldering iron. Do is get a big amount on there and just tin all the pads on the board. At least every one that a component will be soldered to. Alright, so that looks to be pretty much everything tinned. I do need to apply a little bit more flux in some areas, but other than that, we're looking very good. So I'm also going to tin the connector pads up here. We will be soldering the connector on with hot air, but for now I'll go ahead and just tin the pads ahead of time, and then we'll be done. Alright, and the last thing I need to do is just apply a small bit of solder to this center pad right here. just like so. Alright, so that's all the necessary pads tinned, so now we'll just start applying the components onto their pads using the hot air and a pair of tweezers. Alright, so as you can see here, I've gotten the board ready to begin soldering. I've got the hot air warmed up already. So the first thing I'm gonna start out with are these main little capacitors all over here. And of course, this is gonna be a pretty tedious and long process, so I'm just gonna speed through it on the video. But basically, I'm just gonna go through every component and solder it into position. And then once I'm done, I'll show you the final results as well as a couple different things about the board that you might wanna be aware of. So with that, I'm gonna start with these capacitors and we'll just go through and solder everything on. Alright, so as you can see there, I have fully installed all of the passive components, well, almost all of the passive components. There is one more that I need to solder, minus the LED for the drive activity. But up here you can see I've got two resistor positions right here. There's this one up top here and then this one down here. This is for NAND I/O voltage selection. So if you set it to this top set of resistors here, or set of pads here, that will enable the 1.8 volt regulator and supply 1.8 volts to the NAND I/O. And if you put it on this bottom section here, it will supply the 3.3 volt input straight through to the NAND I/O line. So that either will select if you're using 1.8 volt top or 3.3 volt NANDs on the bottom section there. So in my case, I'm pretty sure that the NANDs I'm going to be using are 1.8 volts, so I will be setting the 1.8 volt selection there with one of these resistors. Alright, and as you can see, I've set it to the top position, which will supply power to this regulator, which will supply the 1.8 volt rail for the NANDs. So with that done, the next thing I need to do is solder the connector, and I'm also going to solder the LED at the same time because the LED is very sensitive to heat as well. So I'm going to get this on the preheater, and that way I'll have some bottom heat and I can heat the top at a much lower temperature as to not melt the connector. So I'm going to go ahead and get this in the board preheater and we will go from there. Alright, so I did almost forget, there are some capacitors here on the back of the board that I need to solder as well. So we're just going to go ahead and repeat the same process there and solder on these capacitors. Alright, and now that is all the passive components successfully installed. So with that, like I said, I'm going to get the board on the board preheater here, and then we'll solder the connector. Alright, so as you can see here, I've gotten the board on the board preheater and gotten it up to temperature now. So in order to solder this connector, I'm just going to apply some flux to the board, right where the connector will be. And then we will simply take the connector, place it on the board, and of course we need to fully align it to the pads, just like so. And with it properly aligned, you can just take the hot air at a lower temperature and solder it on. Alright, so that is the connector fully soldered. And while I've got this here, I'm also going to solder on the activity indicator LED. And this is just a green LED that will flash during drive activity. And on these SMD LEDs, if you can make out that green stripe on the bottom of it there, that needs to be inside this little cup shape on the silk screen here. So we're just going to place that upside down like that, or right side up, I guess. And then once it's properly in the correct polarity, we will just solder it onto the pads. And just like that, it looks to be completely soldered. So that is the complete installation of all the passive components, plus the LED and connector. So now I will prepare the board to install both, or the controller, the SM2236, as well as all 4 NAND ICs. So actually, I've already got that pretty much ready to go here. Just keep it on the board preheater. But I do need to take the nozzle off the hot air. So I'm going to go ahead and I'll pause the video here, let everything cool down, and then we will begin the process of installing the ICs onto the board. Alright, so I've now gotten the board on the preheater once again, fully up to temperature. So now we'll start off by soldering the SM2236 controller. So in order to do that, I'm just going to start by applying some flux, just like so. And then we will take it, align it, and then solder it on using the hot air. Of course, I want to make sure it's in the correct position here. And that looks pretty good right there. So I'm going to go ahead and heat it with the hot air. Alright, so that looks nice and soldered right there. So now we'll just repeat the same process, of course, with the NAND chips as well. Alright, so now that the 2 top ones have been soldered on successfully, I'm going to let the board cool down, and that way I can flip it over so the vise isn't covering the pads I need to solder to, and then I'll solder the bottom 2 chips. Alright, so I've gotten the board turned around, so let's just go ahead and apply some flux and solder these bottom 2 on. Alright, so that's all the chips successfully installed. So now we just need to let the board cool down, and then we can connect it to the computer and see if we can actually program it using the SMI MP tool. So I'm going to go ahead and let it cool down and resume the video, and we'll give it a test. Alright, so as you can see here, I've gotten the SSD hooked up to my USB to IDE adapter, as you can see right there, through this ZIF to desktop IDE adapter. However, you can see that I have made some changes to the board after testing it a little bit off camera. Now, it turns out that the NANDs that I had used, those Toshiba NANDs that you saw me install, I had tried those with something else in the past, and I think I overvolted them and killed them, so they did not work properly at all. So unfortunately, I did have to remove those, and I only had 2 other NANDs spare that would actually work with this SM2236 controller. They are 512 gigabit chips, so we should be able to at least achieve 128 gigs, assuming this works properly. But with that said, I've got everything hooked up here, so let's go ahead and turn it on and see if it works. And actually, before I do that, I do have external power connected to this power supply here, because this adapter rather, of course, is designed to power a desktop IDE hard drive, which requires 12 volts. So I have to inject that to turn it on. Of course, this is going to take it down to 3.3 because that's what the ZIF IDE spec is supposed to have. So with that, let's go ahead and turn it on. And that's a good sign. You could hear the Windows new hardware detect sound there. So let's go ahead over to the computer. The next thing we need to do is open the SMI MP tool for the SM2236. You can see I've got it right there. And we'll go ahead and open it up here. And we should be able to select scan drive right here, and in theory it should detect our SSD. And as you can see, it did. It detects that there's Micron flash installed. As you can see, there is indeed 2 Micron chips installed there. There were Toshiba, which, like I said, I removed because they were dead. Now the next thing we want to check here is to see and make sure that all the channels, or the RAM, or the NANDs are detected on all the channels we expect them to be detected on. So if we click this down here, we can take a look, and you can see all 4 CEs on channel A have a device detected, which is perfect. Channel C has one detected on all 4 CEs, and that matches up to exactly how we have them on the board. This is channel A here, channel C, channel B, and channel D. That was the easiest way to route it on this particular board. So in theory, we should be okay to go ahead and program it. So let's go ahead and exit out of this. The next thing we have to go over to here is the parameter tab, and we got to set the flash type in this. So to do that, we just need to select edit config. You have to enter this stupid password, which I really don't understand the point of, but it's 320. And as you can see, all the options became available there. The next thing we need to do is figure out which type of NAND we've got installed. So as you can see, I have the Toshiba selected from before, which didn't work. So we can select auto. You can see the tool found 3 different flash chips that correspond to the ID. And I know that these are 512 gigabit chips, so I'll select that. And in theory, that's the only settings that need to be changed. So go ahead and select Save Config. You can see it'll update the flash in that option up there. Go over to the Test tab, and we'll attempt to program our drive. So it's just doing a pre-test on the flash chips right now to make sure their integrity is good. Hopefully this succeeds. This tool can be a little bit finicky sometimes. So yeah, sometimes it's going to fail. If it does, just restart it. Or disconnect the device, reconnect it. Click scan drive again, and try one more time. And now it's working properly, as you can see there. And as you can see, the firmware was installed successfully. It now registers our capacity of 128 gigs. So everything is looking to be working as intended so far. So I'm going to go ahead and close out of this. We'll reset the drive here, disconnect it, reconnect it. And we'll go ahead and open up disk management. And as you can see, it now detects an uninitialized disk, so we'll go ahead and initialize it as a GPT volume, or a GPT drive. And as you can see, 128 gigs of unallocated space. Go ahead and just create a volume on here real quick just to make sure. And as you can see, the format was successful, and everything looks perfect. So let's go ahead and back over to computer. And there it is, a 128 gigabyte blank volume, which is of course our SSD. And you can actually see the activity LED flash there if I try to copy something over to it. So yeah, our activity LED is working, and these NAND chips are working. But like I said, I don't have enough to populate these ones, unfortunately, but I don't see any reason why they wouldn't work as well. So yeah, that has been the the complete assembly of the SSD. Now for the final test, I'm going to go ahead and plug the drive in to a first generation MacBook Air, a MacBook Air 1,1, 2008 model. I do need to ultrasonic clean it first. As you can see, it has quite a bit of flux on it. But then I'm going to go ahead and try to install a copy of Mac OS on it, make sure it works, and yeah, we'll make sure everything works as intended. Alright, so as you can see here, I have gotten the SSD installed into the MacBook Air. And I've already gone ahead and installed a copy of Mountain Lion, patched of course, because that is required on this specific machine. I've installed a copy of Mountain Lion on here, so we should be able to just flip it over, boot it up, and see how well it works. So let's go ahead and close this up here, and flip the machine over real quick, power it on, and see if it boots. Alright, it chimed. That's a good sign. I am holding down the Option key as you saw, so hopefully it should pull up the boot menu and detect the drive. And as you can see, the SSD is detected, so let's go ahead and boot from it. And as you can see, it has booted successfully. I'm just going ahead and log in real quick. And it is up and running. So let's go ahead and check about this Mac. Let's go to storage first here. Yep, you can see a 128 gig ATA drive. Go to System Report. Go to ATA. And there is our drive right there. I did actually reprogram it with a different name off camera, so it looks better in the system profiler here. But yeah, as you can see, everything is detected. We've got 128 gigs of space, and everything is working perfectly. So the last thing I'll do here is I'm going to go ahead and open up Xbench, and we'll just see what the drive speed is. I don't expect it to be super fast, because at the end of the day it is IDE, which is honestly pretty slow, even UDMA 6, which this drive should be capable of. So we'll go ahead and start that here and see what speed it runs at. And yes, if you were wondering, I did upgrade this MacBook Air to 4 gigs of RAM. That's why it says 4 gigs there, and it did on the About This Mac window as well. I do have another video about that if you'd like to take a look at that. Alright, so there are the speeds right there. You can see I had an uncached write speed of up to 61 megabytes per second. You can see uncached read of up to 81 megabytes per second. And then the random test, we've got a read speed down here of about 80 megabytes per second as well. So that has been the successful assembly and installation and testing of this custom IDE SSD, or ZIF IDE SSD. Now I will, after a little bit more testing, if everything tests out okay, I will publish the design as well as the MP tool and everything else you need to actually assemble and produce one of these drives yourself on my GitHub. Of course, open sourcing the entire design. And I may or may not actually sell these drives as well if there's enough interest. So if this is something you'd be interested in, just leave a comment and let me know. But yeah, that has been the assembly of my custom 128 gigabyte in this case, but it could be 256 gigs with the correct NANDs, IDE ZIF SSD. Hope you enjoyed this video.